Hi, everyone, and hope everyone is okay. Welcome to the Work, Energy, and Power free class with Mr. X that we're going to be doing. It's going to be a beautiful time as we do questions on this particular topic. But first up, let's start with a couple of announcements. And we start off with what is happening in just a couple of weeks' time. We are going to be writing our final examinations very soon. And Mr. X has got huge things happening as we prepare ourselves for the final examination. On the left-hand side, we've got the face-to-face revision classes. These ones will take place for a period of 4 days. It's you and me face-to-face, 8 hours a day from 8 a.m. till 4 p.m. For the whole 4 days, it's going to be 1,000 Rand per subject. As you can see, there's 3 groups there. Maths Group 1 starting from the 21st to the 24th. Maths Group 2 from the 29th to the 31st. And also on the 3rd to make it into 4 days. And for Physical Science, we only have 1 group, 5 to the 7th, and also the 10th of November. Please note that space is limited. So the sooner you actually do this, the better. If you'd like to know more, please do DM me so I can give you more information. But what I can tell you is that people are booking already. They're coming for the face-to-face revision classes, 8 hours a day. And I'll tell you, we only have 2 breaks, each 15 minutes, 7.5 hours. We are on fire, like seriously learning and preparing ourselves for the final examination. On the right-hand side is an alternative to what we're doing. So if you can't see me face to face, don't worry, I got your back as always. I will be hosting the online revision program with Mr. X. Unlike the face to face, the online revision program is going to be 20 hours of revision, and I've set up the times and the days, and it's going to be on Zoom. It's 500 rands for a subject. So if you'd like to do both of them, you're looking at 1,000 rands. If you want to do one, that's 500. For the face-to-face, if you'd like to do one, it's 1,000. If you'd like to do both, it's 2,000. Space is limited, as I said, so please make sure you pull through. For the face-to-face, we'll be doing it at Damelin College in Braamfontein, and the venue is that place there. And you can see I also put it on the poster right there. It's a game changer. We will change our lives using this program. And as I always say on the group, I can save you. All right. Now, that being said, let's do the physics. Now, we're going to do the topic work, energy, and power, and we're going to run through it via questions. So I'll start with something basic, build up, and get more and more and more and more. As always, during the course of our interaction, if you do not understand something, you can always type and ask, or you can lift up your hand, but allow me as much as I can to flow as we work together. I'm ready, and I hope you're ready. Here we go. Our first question, write down the title. It's the 2022 Free State Prelim Paper 2, and it's question number 5. Please do write down the typical title for this question. And it reads to this extent. It says to us, block X of mass 4 kilograms is initially at rest at the bottom of the incline. It's important to translate the English into physics. At rest initially means that its initial velocity is 0, which makes an angle of 25 degrees with the horizontal. A 78.4 Newton force acting parallel to the incline pulls block SX up the incline. So from what we're learning, the block is moving up the incline. We're also told that block X experiences a constant frictional force of 13 newtons. Our first question, and in most cases, is usually a definition. 5.1, define the term conservative force in words and give an example of such a force that is acting on X. Now, it's important to note that when you are dealing with definitions, it's either you'll get 2 marks or 0. They are very strict when it comes to definitions. So you must know them by head. You will find them on your exam guideline, but here's the idea. They say to us, define the term conservative force in words and give an example of such a force acting on block S. It is a force, and I'm defining, for which the work done, okay, in moving, and you must write this as I pull through, in moving an object between 2 points is independent of the path taken. Now, in the regard to the example, the best example of a conservative force would be the gravitational force. So the gravitational force becomes the example, because even on this particular object, the gravitational force acts on that particular object. And so the definition and the example of the force acting on block X, which is a conservative force, is what you see there. Let me try 5.2 quickly so that it is easier to pull through from there on. I'm ready for this one here. 5.2. 5.2 says, draw a free body diagram indicating all the forces acting parallel to the incline. All right, so it says, draw a free body diagram integrating all the forces parallel to the incline that are acting on that block. They said parallel to the incline. So it's important to be able to draw according to what they have given you. Do not over-answer. Please do not over-answer. So here is what you have. Usually for 3 marks, we would require 3 forces. So you'd have this force, which is obviously the applied force. So you can write it as F, or you can say force applied in that regard. And then you also have another force, which is the force due to friction. By the way, frictional force is a force that opposes the motion of an object. There's usually a problem whereby sometimes you may think that the force due to friction opposes the applied force. That is not necessarily true. The force due to friction opposes the direction of displacement of the object. In other words, if the object is moving upwards, then the force of friction will act downwards. In the same breath, if the object is moving downwards, then frictional force acts upwards. If it was to the right, friction will act to the left. So it's important to understand which direction the frictional force will act. It acts opposite to the motion of an object. Here we go. Let's break it down. There's another force. I want you to understand, because the object is on an incline, the force due to gravity is broken into its typical components. Namely, there is the force of gravity perpendicular and the force of gravity parallel. Now I'm going to draw everything, then I'm going to take out the ones which are not parallel, as the question wants only those that are parallel. So you'd have something to this effect. This will be your normal force. Then the force of gravity parallel would be a downward force, and its direction will be downward always. Listen to me. Regardless of whether the object is going up, the force due to gravity parallel would always act downwards And yes, it's a parallel force. So if you were to draw the free body diagram, including everyone, this is what you would do. But because they want parallel forces, then your story ends up like this: 3 forces, 3 marks, and that becomes your answer in this regard. There's a question that says, does the mark allocation show how many forces you need to draw? Yes. In most cases, if not 100% of the times, yes, it does. For 3 marks, we may require 3 forces. Now, just as a heads up to add some extra info on this, listen to me. If they just asked you to draw the free body diagram, just the free body diagram, without mentioning parallel or whatsoever, then you would have done again in the same breath. You have your force applied, you've got your frictional force, you've got your normal force, and then you will have this one here as your force due to gravity, your applied, your normal, and your force of friction. Usually in such a question, they would have said this is 4 marks for 4 forces. Notice that here in this diagram, I did not put our force of gravity parallel, our force of gravity perpendicular. You can. But when you do, please remove the FG and then put its components. Put its components if you decide on it. But usually for 4 marks, you would probably need to just leave it like this. But when you're doing the calculation, please ensure that it is inclusive of our force due to gravity parallel and our force of gravity perpendicular. In most cases, the force of gravity perpendicular and the normal force, they cancel each other out. So basically, that's your story. So to answer our question, here's where we are. Please keep that in mind. I'm ready for 5.3. Here we go on 5.3. Using energy principles only, calculate the speed of block X after it has moved up the incline. Here's a disclaimer from my side. There are about 5 ways of doing this, if not 6 different ways of being able to do this. And so I'm not going to run through all the methods, just do one method or so, and then we take it up from there. The question says use energy principles. So you are at liberty to use a formula that has the concepts of energy in it. Let me just list down a couple so that you can see where you would align yourself. You can use this one. Work done by a non-conservative force is the change in the kinetic energy and the change in the potential energy. That's also doable. Or you can use my favorite, which is the net work done on an object is the equal to the change in the object's kinetic energy. This is coming from the fact that you are dealing with the work energy theorem. Usually when we deal with the work energy theorem, this is what we use. Work net is equal to the change in the object's kinetic energy. Now, when it comes to this one, work net, the word net means sum of. So when you say net, you're talking about sum of. You are adding all the works done on the object. Since we drew the free body diagram, notice that the vertical forces, namely, and this is something I'm going to do in a bit later on. So when we drew our free body with something to this effect, that, then I'll just put the components as well, that. Notice that the vertical forces, which is this one, normal force, and that one, force of gravity perpendicular, they do no work on the object because their theta is 90. Let me explain. The formula for work is F delta X cos theta. So these particular forces, these vertical forces, they do no work on the object. Why is that? It's because they act perpendicular to the direction or the incline. So the angle is 90 and mathematically cos 90 is 0. So the only significant forces that are doing work is the work done by the force F and the work done by the force of friction and the work done by the force of gravity parallel. Those are the typical forces that are doing work on that particular object. Fine. I'm going to come to your questions. Allow me to move through on this one, and we will take it up from there. All this is equal to the change in the kinetic energy. So I'm using this formula. The work net is equal to delta K. The rest is just numbers and formulas. Work done by force F will be force F, F delta X cos theta. Work done by friction is force of friction, delta X cos theta. Then also you have the work done by gravity parallel is Fg parallel delta X cos theta. All this is equal to the change in the kinetic energy, which is a half mv F squared minus a half mvi squared. I'm trying to lay some basics here so that when we start doing questions, it becomes easier, or rather when you go deeper, it becomes easier to understand. The rest are numbers, but let me just talk about this guy. Fg parallel. Fg parallel is mg sine theta. So please remember this formula. Fg parallel is actually mg sine theta, where theta for this particular sine, this theta, is the angle of inclination, namely 25. So to rewrite this, I would then say F delta X cos theta, then plus FF delta X cos theta, then plus mg, I need to Fg parallel, mg sine theta, then delta X cos theta is equal to a half mv F squared minus a half mvi squared. The rest will be algebra. Now remember this, the theta for cos, the theta for cos is the angle between the force and the displacement. Clarify with me, work with me. If the object is going upwards, all right, so this is the direction of the object, and the force acting on it is also acting upwards like this. So the force acting, in this case, force F, and the direction of displacement of the object up the incline, they are the same, then theta, the angle between them, is 0 every time. But if the force and the displacement are opposite, just like in the case of frictional force, just like in the case of force of gravity parallel, if they are opposite to the displacement, then U theta is 180. Let's put numbers. Let's get down to business. Here we go. F, the number, 78,4. How far did the object go? 3 meters up the incline. And then what is the theta? Where is F acting? Upwards. Where's the object going? Upwards. What is the angle? 0. Here we go. Force of friction. The question told us that frictional force is 13 newtons. Numbers 13. Also times 3 times. And because friction acts opposite to the displacement, it's now cos 180 plus mass of the object 4 grams. All the information is given. G 9.8, all right, times sine the angle of inclination. I remember telling you, Guti, the theta for sine is the angle of inclination, which is 25 times delta x. How far did we go? 3 times cos. Force of gravity parallel is acting opposite to the displacement. That is 180. All this is equal to a half mass for final velocity. That is exactly what we're looking for. We're looking for the speed of the block after it has moved 3 meters. So then the maths, bf squared minus a half, the mass 4. But initially, we were at rest. So therefore, my initial velocity is 0. Then the only variable that we don't know is VF. You do the maths properly, and after square rooting, can't do the maths with you here. This is something that you can do. My answer, you can confirm, 8.56 meters per second. That's the basic idea from there on. All right, I'm happy that people are even helping each other on the chat there, just to make sure that everything is cleared up nicely right there. All right, I'm about to go. Let's do our next question. So this was the basic one, and I did try to explain a couple of things in it, just to make sure that everything is clear. It's been confirmed, 8.56. Thank you so much. Write this down, or you can take a screenshot of this and we can take it up from there. The question says, do we include direction? No, we don't. In this case, they say the speed. So we're looking at the value, the magnitude only, and that one is aligning to 8.56. Taking this out in the next 5 or so seconds so that it's easier. All right, I'm now going to up the game. More questions. The more we do, the more we know. The less we do, the less we know. A question is speed the same as velocity? No. Velocity is a vector quantity. They will have the same magnitude, but when we speak about velocity, we will entertain the idea of direction. So the magnitude, the values will be the same, but the directions would be different. 2010 November, paper 1, question 5. Please write that one down. It's gone. It is gone and is going. 2010 November, paper 1, question 5. One of my biggest issues with you guys is I need you to be able to read a question properly. Learn to read and mark the important stuff. Read a question properly. They give a lot of information. It's available, and we'll be using it right there from there on. Here we go. A worker pulls a crate of mass 30 kgs from rest. We translate English into physics. From rest along a horizontal floor. In the previous question, we were dealing with an inclined plane. Now we're dealing with the horizontal plane. By applying a constant force of magnitude 50 newtons at an angle of 30 degrees to the horizontal. A frictional force of magnitude 20 newtons acts on the crate while moving along the floor. Sharp question. Draw a labeled free body diagram to show all the forces acting on the crate during its particular motion. Free body diagram. Just as a teaching moment, listen to me. The free body diagram and the force diagram are two different types of diagrams. So in the free body, we denote or we show our object using a dot. That's the free body diagram. In the force diagram, we show our object using something that looks like a boxing yana, as can be seen. They asked for the free body diagram, so we'll use the dot. All the forces acting on the object. Let's start with the basic ones. Horizontal, so this would have to be force of gravity there. So I'll write it here as Fg. Then we've got another force, still vertical, and that force should be the normal force, which is Fn. Then since the object is being pulled, and so it's moving, and judging by the diagram, its direction is to the right. So therefore, there is a force responsible for the movement of that object, and this force is F, which is the 50 newtons, and I'll just call it the applied force, or force F, if you may. Notice that I put it at an inclination. Now listen to this. The object is on a horizontal surface, but the force acting on the object is inclined. Those are two different things. The object surface is horizontal, but the force responsible for moving the object is acting at 30 degrees to the horizontal. It's a force inclined. Since the object is moving ultimately in this direction, I'm seeing what I'm seeing. Use said to us earlier on that there is a force that opposes displacement. Its name is force of friction. 4 forces, 4 marks. Write this down. Somebody may be asking, say, is it necessary to include the angle and write 30 degrees? No, it's not. It's not a harm to do that, but you don't have to. So please note that in that particular regard. That's 5.1. 5.2, I see some of your questions. I'll answer them on 5.3 because it will cover up what you guys are asking. Please note that when the object is on a horizontal surface, we don't have our force of gravity parallel. The force of gravity parallel exists under the situation where the object is on an incline. But here, it's on a horizontal. What is inclined is its force. And that will give us a lot of situations to deal with because the force is inclined. 5.2, here we go. Give a reason why each of the vertical forces acting on the crate do no work on the crate. They do no work on the crate. I remember saying something to this effect. So maybe you could say they act perpendicular, okay, perpendicular to the displacement of the object. Yes. And then maybe just to add more flesh into this of the object, you could also write the formula that we know about work and say work is F delta X cos theta. And then the theta that we have is 90. So cos 90 would be 0. And therefore, the work done would also be 0. So please keep that in mind. so that you can pull through from there on. So write it down and make sure that you understand this. Speaking about zeros, Speaking about zeros, listen to this. In this topic, and maybe even in any other topic, when you read a phrase and the phrase says constant velocity, even if they say constant speed, either or, then the following applies. At constant velocity, at constant speed, the net force acting on the object is 0 newtons. And this comes from the fact that at constant speed, the acceleration of the object is 0 meters per second squared. Newton's second law says F net is equal to mass of an object and its acceleration. So if the acceleration is 0, then by extension, the net force is 0. Please remember that. One more time. At constant velocity, what is the implication? Net force is 0 newtons. Why? Because the acceleration is 0 at constant velocity, net force, which is ma, becomes 0. Also, by extension, when the constant velocity phrase pops up again, the net work done on the object will also be 0 joules. So under the situation where the constant velocity is the phrase available, the implication, net force 0, okay, acceleration 0, all right, net work is also 0. So as you read, please take into cognizance that situation. And further on as an extension, you see, when you say constant velocity, you are saying to yourself, I've got a point A and I've got a point B. And so the object at this point A has 20 meters per second. At point B, 20 meters per second. So there was no change in velocity. The velocity is constant. The initial velocity, the final velocity, the velocity at A, the velocity at B, both of them are equal. It's constant. It's unchanging. In fact, the change in the velocity is 0. What I have at A is what I have at B. My change is 0. Fine. 5.3, here we go. The math begins on 5.3. As a further extension, is the change in the kinetic energy also 0? Yes, it is right there. So everything is 0 in that regard. The question, calculate the net work done on the crate as it reaches point P, 6 meters from the starting point O. 4 marks. Follow my lead and hear me out. 5.3. So I want you to understand this. You're looking for the net work done on the crate. So we need to interrogate which forces are doing work on the object. So let me go back to my free body diagram and I will pick up what I see and the forces that are doing any significant work on the object. We agreed that normal and his cousin brother gravity are doing 0 work. Why is that? Because they act perpendicular to the displacement. Now, the applied force is giving us a bit of a problem. It's acting at a certain angle. Now, when a force, this breathes into application to Newton's laws. So there's a connotation to these two topics. Now, when a force acts at an angle, it is broken down into its components. In the context of this question, this would be the Fx, the horizontal component, with a formula of F cos theta. So it will be F applied cos theta, where the theta is the angle 30 degrees upon which the force is acting. Similarly, we have another force that comes as a result of the inclination of Fa, is called Fy, which is the typical vertical component. Upon formulas, it is Fa sine theta. So in this regard, about theta would be the 30 degrees, which is this angle of inclination upon which the force is acting. If this was the topic, application to Newton's laws would have been dancing on Fn, Fy, and Fg. But suffices to say that Fn, Fy, and Fg, since they are vertical forces, they do no work on the object. So the only guys doing work is the force X, which is the horizontal component, and the force due to friction. What am I looking for? I am looking for the net work done on the object. So the net work done, who's doing the work, is the work done by Fx. Who's doing the work is the work done by the force due to friction. Let's do some maths and break it down. Ff is Fx delta x cos theta plus Ff delta x cos theta. Put numbers with me. Let's go. So Fx, from what we said is the force applied and cos theta. That's what Fx is. Force applied cos theta multiplied by, this is delta x cos theta. It continues Ff delta x cos theta as well. So there you are. Perfect. Numbers we put, then we can get our answer. The applied force is the 50, and then I'll write this as cos 30. Please do remember, Uti, this theta for the horizontal component is the 30, but this theta is the angle between the horizontal component and the displacement. So how far did we go? OP happens to be 6 meters multiplied by cos theta, and where theta is the 0. Oh, say 0? How? It's because E, Fx, ne displacement are both moving in the same direction. Plus Ff, force due to friction, whose value is 20. Delta x is 6. Then frictional force is always acting opposite to the displacement. So it's 180. Maths the rest, 139,81 joules. That is the net work that is done on the object. Perfect, right there. I said earlier on, there's about 5 ways of doing this. And so I would not go through all the 5 ways, otherwise we'll end up doing very much 1 question or 2 questions. But basically, this looks like this. There's about 4 or 5 ways of actually doing this that you can actually get the answer. I will send memos to this, and you can align yourself to whichever method you would want to work with. All right, I'm ready from the first one there. Somebody says, say, what if I use the force applied as a wall, then my angle will be cos theta? Yes, you can do that, but you would get away with it, and I'll tell you why. It's because the cos theta is cos 0 and cos 0 is 1. But if in such a case that the applied force was opposing the displacement, that will really give you a bit of a problem on that. So yes, you can. Mathematically, it works in that context. Go ahead, I'm listening. I've unmuted you. You lifted up your hand. All right, let me continue in that regard. Perfect. Here we go. Let's try another part. Right, 5.4. 5.4 says, use the work energy theorem to calculate the speed of the crate at the instant it reaches point P. The work energy theorem says net work is equal to the change in the kinetic energy of the object. So we're looking at half mv f squared minus a half mv I squared. That is your network. But then I'm looking for the final velocity upon which the object reaches at point P. So since we found from the previous question, E network is 139.81, we may quickly then say half the mass 30, then the final velocity. This is the one that I do not know, minus a half the mass 30, then the initial velocity in that regard is 0. And why I'm saying so, it is from rest. So when it started at point O, it was at rest. The rest is algebra, it's mathematics. Done properly, final velocity is 3.05 meters per second. That's 5.4. Let's try 5.5. Let me read some of your questions so that it's easier to pull through. All right, perfect. I see some of you guys are helping each other in the chat. Very proud of you. 5.5 is a bit interesting, so let's go deeper on 5.5. It says, the worker now pulls or now applies a force of the same magnitude, but a smaller angle. So the force is still 50 newtons, but the angle is less than 30 degrees. Same force, but a smaller angle on the horizontal. Okay, question. How does the work done by the worker now compare to the work done by the worker in question 5.3? Write down greater than, smaller than, equal to, and give a reason for your answer. Perfect. So, hear me out. The angle theta has been decreased. So, theta decreases. Don't say eases, it decreases right there. And so, because of that, the implication is that, and this comes also from the topic in mathematics, trig graphs. When theta decreases, then cos theta will increase. All the time, try it in your calculator. If, for an example, you put cos 30, you should get 0.866 something, sharp. Put a smaller angle, this time put 20, you get 0.939 something. It looks like if I decrease the angle, I increase cos theta. And the formula for work says work done is the force acting delta x cos theta. In the context of this question, the force is the same like before. How far we went is the same like before. But what is different is the angle. Since theta decreased, then cos theta increases. And since the only factor, every other factor is remaining the same. Force the same. Distance the same. Theta not the same. has decreased, cos theta has increased. By virtue of that implication, it would mean, therefore, that the work done will increase, and the word that they wanted is greater than. One more time, let's go back and get this right. What decreased? Theta. Okay, sure. So what increased? Cos theta. Remember that the work done by the worker, since it's acting at an angle, is Fx. And so Fx, from what we said, is Fa, the applied force, cos theta. And I'm giving the implication that the moment this guy has increased, this particular guy has increased, then it has decreased, sorry, then it means cos theta will increase and Fx will increase, which in turn will give rise to a bigger typical work done. Let me write this down again. Let me explain it again. Listen to me. Let me start this way. Maybe this will make a bit of some sense. The force by the worker that is doing any work is the force applied, delta, force applied, let me take cos theta, because it's the horizontal component. And Use says theta has decreased. So what does that mean? It means U cos theta will increase. So the horizontal component of this force will now be greater. Maybe that's a statement I need to put across and say the horizontal component will increase, And so just to pull across then, check this out. The work done is the force X, delta X cos theta. In the initial part, when I explained this, I put the theta here as the one for F, but maybe make it a bit more clearer to those that may be a bit struggling on this. So basically, the Fx is your Fa delta X cos theta, then I'll write and then say delta X cos theta there. So these guys don't really change. And then this one is the one that has changed. So cos theta has increased, and then work done will also increase. At the worst case scenario, here's what you do. Try to calculate. They said no calculations required, but at the worst case scenario, do it. Put theta as 30 as they gave you, and the answer for 5.3. Then put theta as a smaller number, then you'll see that the work done will increase. So just to reiterate, you can write it like this, and you will get your answer. So as a conclusion, the work done will increase. In the exam, please don't write shortcuts, guys. They don't like it. Please do write full words. I'm just doing this now, but always write full words. Let's try another question together, and then I'll probably give you one to try, and we take it up from there. Work with me. Let's go to our next one. Let's keep pulling through. Say, does this apply if the object is on the inclined plane? It will only apply if the object is on the inclined plane and the force acting is also an inclined force. Let me show you the scenario that way this concept will apply. Let's say you've got an inclined plane like this, and then on that inclined plane, there is an object, and then on that object, I saw this in a question, I think it was application to Newton's laws. On that inclined plane, there is an inclined force on the object. Then yes, that would definitely affect the force or the work done by the applied force when you change the angle theta, which is the angle of inclination between, or rather the angle upon which the applied force is acting. I'm ready for my next one. Let's go. 2015, the Gauteng paper. This one is a very interesting question, and I'll run through this. Then maybe work on something else, and we go ahead. So far, I hope everyone is doing okay. Write down the title, 2015 Gauteng Prelim, paper 1, and it's question 6. Here's my belief. The more you do, the more you know. The less you do, the less you know. And here we are, we want to do more. The story. A box of mass 86 kilograms is accelerating down a surface inclined at 25 degrees to the horizontal. Hear me out. The box is accelerating down. On the object or on the diagram, this looks like the applied force. But in the applied force, in the presence of the applied force, the object, according to the question, is accelerating or moving downwards, even when there is an applied force. So this is a classical situation where in the presence of an applied force, the object is not moving in the direction of the applied force, but rather opposite it. Okay, the story continues under the diagram. A man applies a force F upwards, parallel to the plane, in an attempt to prevent the box from sliding down the inclined plane. In spite of the man's effort, the box is accelerating down the inclined plane. So again, it does not always follow that the applied force, its direction will be the same as the direction of this particular object. In this case, applied force goes up, but where is the object going? Down. Imagine this, okay? Let's say a child was going up an incline and trying to pull something upwards, but that thing is too heavy for the child, so the thing keeps going down. Imagine that scenario as something to this effect. Let's go. 6.1, the question. What is a non-conservative force? What is a non-conservative force? Here we go. And the definitions are 2 marks, I keep saying, and you must know them by head. A force for which the work done, okay, in moving an object between 2 points, moving an object between 2 points, comma, is dependent on the path taken, dependent on the path taken. All right. So in the other question, I think it was my first question, we defined a conservative, and the example that we gave was gravitational force. In this context, the conservative force would be force of friction. The non-conservative would be force of friction. So please keep that in mind. In fact, it's the best example of a non-conservative force. The path taken actually matters. So the work done by frictional force, by a non-conservative force, is dependent on the path taken by the object. I'm ready for the next one. 6.2. Here we go. It says to me, the coefficient of kinetic friction given by this symbol, which is read as mu k, between the box and the surface of the plane is 0.22. All right. Prove that the magnitude of the kinetic frictional force is 168.04. Perfect. Now, your context will give you how to use the question. The formula for friction, kinetic friction, would be the coefficient of kinetic friction multiplied by the normal force. But I want you to hear this out. On an incline, The normal force, let me start here. On a horizontal surface, the normal force is just mg. That's a horizontal surface. On an incline, the normal force is mg cos theta. That's an inclined surface. And the theta is the angle of inclination. Angle of inclination. That is the theta. Please remember this. Contextually speaking, the normal force changes depending on the surface of concern. Since we're dealing with the typical inclined surface, I can then rewrite it as mg cos theta, and they want me to show that the kinetic frictional force is 168,04. Maths, here we go. 0,22, I'm ready. The mass of the object is 86. They gave me G 9,8, and then the theta, angle of inclination, is 25. Please do confirm if the answer is exactly what they gave us. Talk to me. Is that a yes or a no? Let me see if it's true or not. Is my kinetic friction what they gave me? It's a yes for you guys. Appreciate that. Let's go to our next one. Talk to me where you didn't understand, but I'm hoping that you guys are seeing, because as I teach, I'm trying to add some more info so that you guys have an idea where all of these things are coming from. Thank you. Appreciate. 6.3. Another definition. This one definitely usually comes out almost always. State the work energy theorem in words. State the work energy theorem in words. That's what this particular statement is saying. Somebody says, would it be correct if we were to work out normal force first? Yes. But remember, in normal force would be mg cos theta, right? Please remember that. The story. We're stating the work energy theorem in words, and so it says the following. Another 2 marks that we need to know. The net work done, or you can say the total work done, the net work done on an object, okay, is equal to the change in the object's kinetic energy, energy. Basically, that's the work energy theorem in words. We try the next one, 6.4. 6.4. 4 marks. Let's go. Draw a labeled free body diagram of all the forces that are acting on the box. The free body diagram ultimately helps you to be able to calculate for whatever situation you are given. Because from the free body diagram, you can tell the direction of the force. And so you can tell the theta, cos theta for that particular force depending on its direction. So here we go, and we're pulling through from here on. So there is the applied force, which is not moving the object in its direction, unfortunately. There is this one here, the normal force. Then this one would be the force of gravity. Then since the object is going downwards, there is another force opposing its displacement, which is the force due to friction. What I love about this question is that classically, it shows you a situation where the applied force and the frictional force are actually in the same direction. You see, I didn't break down the force of gravity into its components. I did not. I would, however, when I'm doing a calculation, especially in 6.5, I would, however, use the force of gravity parallel. In fact, the very reason why the object is moving downwards is due to the force of gravity parallel. By contrast and comparison, the force of gravity parallel is bigger in magnitude than the force F, causing the object to actually prefer to move downwards in spite of the presence of the applied force. This must be cleared up. Follow my line of thinking right there. And I'm saying to you, the object goes down. Yes, sir. It goes down. Where does friction act? It acts opposite to the displacement of the object. Where is the object going? Down. Where should friction act? Up, up. Okay? Opposing the displacement. And again, this is a classical situation where the force applied and the frictional force are actually in the same direction. And the reason why the object is going down again, and I'll use a different color, is due to the presence of force of gravity parallel, which is acting in a downward direction like this. I didn't put it in the free body. I'm just showing you where it would be. And upon calculation, I would need to use it. Force of gravity parallel in that regard. So if you were to draw the free body diagram, it would be all the green arrows, but the force of gravity parallel just simply shows you that in its presence, the object in this case would move downwards. All right, write that one down. Let me move on because I want to do 6.5 and all that. Somebody says, so if the question was 3 marks, would you have excluded normal force? Maybe not. Yeah? Maybe not. I would rather have you write everything and rather over answer than under answer. So if the question gives you 3 marks and they say write all the forces, but when you see that there's 4 forces, write all 4 of them. You are better off over answering than under answering. All right, so I'll give you that in that regard. But usually the amount of marks will give you an indication for the amount of forces that you need to draw. Go ahead, I've unmuted you. I'm listening.
Good evening, sir.
Hi.
My question is, since whatever this thing is, the object is moving downwards in spite of the effort to push it upwards, does this mean that the FG parallel is bigger than the force applied?
Yes, that's what it means.
Oh.
Yeah, that's what it means.
Okay.
I did reiterate to that. Definitely, it means exactly that. So that would be
okay.
the answer. Yes, it means that. All right. So
thank you.
All right. You're welcome. So in regard to the question asked, I want you to get this right. The object's ultimate direction will be in the direction of the force with the greatest magnitude. Objects will move up or down depending on the force that is acting on them. If the upward force happens to be the greatest in the parallel section, then definitely the object will go upwards. So objects will move in the direction of the greatest force in this particular situation. Go ahead. I'm all ears. 6.5, I'm ready though. I have unmuted you. All right, I'm not hearing you, so let me go for 6.5 and maybe type your question. I'm reading. The box accelerates parallel.
Yes, sir. Sir,
okay, sharp, perfect. All right, I'm ready. So the question says the box accelerates parallel down the inclined plane for a distance of 0.9 meters at 1.54 meters per second squared. This value is the acceleration. Use the work energy theorem and calculate the work done by the men on the box. So true to the situation, the object is accelerating at 1.54 meters per second squared, and it covers a distance of 0.9. And we are using the work energy theorem to calculate the work done by the man on the box, 5 marks. Let's do some maths. Listen to this. The net work done on an object is equal to the change in its kinetic energy. This would be the work energy theorem. And who is doing work on the object? So according to the free body diagram, it has to be the force F. It has to be the force of friction. It has to be the force of gravity parallel. Remember that in the calculation segment, we will include force of gravity parallel. Obviously, the normal force and the gravity perpendicular are opposite and perpendicular, so they give us a work done of 0. So to put it into context, work done by force F plus work done by force of friction plus work done by gravity parallel, all this is equal to the change in the kinetic energy. So to put numbers again, I'll still keep going old school. Force F delta X cos theta, then force of friction delta X cos theta, work done by gravity parallel. I remember Use said it's mg sine theta right there. Mg sine theta, mg sine theta, delta x, where's my pen? All right, found it. Delta x cos theta. All this is equal to the change in the kinetic energy, which is half mv f squared minus a half mv I squared. Sharp. We put numbers, please. We put numbers there. Remember, I'm looking for the work done by the man on the box. So I don't know the force of the man. I don't. But I know the work done. I'm looking for the work done by the man, which is work done by F. So I did put it broken, but I'm looking for the work done by the man. So I'll just write it as work done by F. Then I put the numbers here. The frictional force, I think from the question that we asked in 6.2 was 168. So I'm going to put my numbers, comma 0.4. How far did we go? 0.9 meters times cos 180. Cos 180, because the frictional force always opposes the displacement. Then m, the mass of the object, I think should be 86 G 9.8 times sine 25, that angle, times U delta x, which is 0.9, times cos 180, oh no, cos 0 actually here. Why cos 0? Because the force of gravity parallel is acting in the same direction as the displacement of the object. All this is equal to a half the mass of the object, I think should be 86 VF squared, don't know, minus a half, then 86, then VI squared, also don't know. We have a problem, a big problem. Look at this. In the expression, OWF, we don't know. We don't. And also in the same regard, we don't know VF squared. We don't know VI squared. We don't know anything along those lines. So we've got 3 unknowns in this situation. WF, work done by the men, final velocity, VF squared, and VI squared. We don't know. But here's what we know. Oh, let's get clever this. We know the acceleration. They gave us. We know how far we went. They gave us. Now, listen to this. You can always use equations of motion. You can. You see, in the equations of motion, and I'm going to relate something that is this part and that part. We have a formula that says VF squared is equal to VI squared plus 2A delta X. I'll just call it delta X because this is not vertical projectile. Delta X, how far the object went. So you can use these formulas. And when you do, then OVF squared minus VI squared is actually 2A delta X. Okay, say, you took this to the other side. Yeah. But how does it help us to get what we need? We're almost there. We're almost there. Look at this. The A is acceleration, 1.54. The delta X is 0.9. The VF squared minus VI squared. So then the VF squared minus VI squared is 2 times 1.54 times 0.9, which gives you an answer for 2.772. Then to bring it home, now that we know this, you see, look at this part here. Look at this part. Is half 86 VF squared minus half 86 VI squared. So what is common here is actually half times 86. When I take it out, I've got VF squared minus VI squared. And what is this VF squared minus VI squared? Is 2.772. So you can always use equations of motion and you're able to get your answer. And why I use that is because when they showed me this, again, there's many methods to this, okay? When they showed me the 1.54, in my head, I'm like, I have acceleration and I've got how far I went, but I don't have OVF squared. I don't have OVI squared. And I'm looking for the work F done by the man. That's what I'm looking for. So then from that perspective, now the only guy that I don't know is work done by the man. Okay, so then I can bring it home right here. Talk to me. I'll read your questions now, and let's see how far we go. Perfect. Let's bring it home. Let's bring it home. Who WF don't know you, plus, and I think you can get numbers to all of this. I think this one here, this one should be negative 151.236, if I'm not mistaken, this part here, plus this one of the force of gravity parallel, plus 320.56 is equal to half times 86 times OVF squared minus VI squared, which is 2.772. There you are. Then finally, you're looking for the work done by F. I get negative 50.13 joules. And it makes sense why the work done is negative. It's because the force F is moving in a direction opposite to the displacement. So when a force moves opposite to the displacement, the work that it does on an object is actually going to be negative. And so look at the force of gravity parallel. Somebody asked and I read where they said, but why is force of gravity parallel positive? Why is the work done by force of gravity parallel positive? My answer is, it's because it's acting in the same direction as the displacement. So U theta here is 0. So cos 0, which is just a positive one, hence the work done by that particular force of gravity parallel is a positive force. All right, perfect. Write this down right there. All right, let me hear some of the questions. All right. Okay, Sama just answers to some questions being asked. Is work done directly proportional to cos theta? No, not at all. is proportional to the force, to the displacement, and to theta. In the case of the question that I did prior, the reason why I used cos theta as directly proportional was because it wasn't even directly proportional. I said cos theta affects the work done is because they told us that everything else was remaining as constant. So that's why you have it along those lines. Again, I repeat, there is many ways you can do it. You can even choose to use F net is equal to MA. You still get the same answer, blah, 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 blah. Go ahead. I'm listening right there.
Thank you, sir. I've been answered.
Okay, perfect. All right. So another thing that's very important, guys. Somebody's asking, why is work done by friction negative? It's because it opposes displacement. Let me give a simple statement. If a force is acting in the same direction as an object, then its work done would be positive. And similarly, if a force acts in a direction opposite to the displacement, its work done would be negative. So keep in mind upon which scenario you have so that you can pull through according to the understanding. Hence, we have it along those lines. Perfect. It's good to learn many methods. Let's go to our next question. I so want to give you a question. I so want to give you a question right now. Something to try and work on and pull through from there on. I'm about to take this out. Yeah. Type she. Somebody says physics is so respectful. It's so demure. Oh, Bastian. It's so QT. When you're working with Mr. X, I got your back. You guys should see me when I'll be doing the revisions. I will be literally fire. Type she. In fact, I will be fire, not literally on fire. I will be fire. Oh, kaparipipipi. Hepepepepepe. Fire. Okay, somebody's got a hand. Go ahead. I'm listening. I'm listening. I've unmuted you.
I can hear me, sir.
Yes.
Can you leave our work done as negative or?
Oh, okay. Yes, you can leave your work done as negative. Because work is not a vector quantity, it's a scalar quantity. It doesn't have direction. So yes, you can leave it as a negative 50.13. All right.
Thank you.
Perfect. Along those lines, let's go further. All right. I need to move, guys. Somebody's asking a question. Let me hear that. Go ahead. I've unmuted you.
Sir, can I ask, is it possible to do it using
Get close to your
FNet
mic. I can hardly hear you.
Is it possible if you can do it with FNet is equals to MA?
Yes, you can. You can do. There's many methods to that. That's what I was saying to you. You guys, there's thousands of methods to doing this. And if I try to do, there's about 5 methods of doing this. If I try to do all of them, oh my word, it's going to take us the whole time and we will not be able to win on that one. All right. Somebody says, sir, please repeat what you said about forces acting in the same direction as the displacement. I said, if forces act in the same direction as the displacement, then the work done is positive. That's what I said. So just to reiterate, some people are asking, okay, what's the implication? Let me do this. What if the object was moving up? Guys, if the object was moving up, then the applied force would be positive. Then the friction would act down. Then the gravity would always act down. Friction and gravity would be negative. Contextually to your question, it depends on the information that has ultimately been given. All right, I'm ready. Let's move on. I want to skip this one here and come to this question because I want you to try this question. I want you to try it. It's a 2020 Free State paper. I'm going to give you about 6-7 minutes to try the question get a bit more involved. I've been talking the whole 1 hour over minutes. So now it's you. Try it. Try, Chuck Norris. Try. 6, 7 minutes. Let's go. 2 more minutes. 2 more minutes. All right, let's do this. 2020 Free State Prelim Paper 1, and this question number 5. Let's see how far we go. Somebody says I got a catastrophic bombastic velocity. Aibo, Pastor Enigma. Kwenzakalani? Angithi ukundile. Yeah, kodwa ungatrim. It is written. Let's do this. Right there. All right, here we go. I'm ready for this one. Bombastic velocity, catastrophic. Aye, Sugamatot. The diagram below, not drawn to scale, shows a trolley of mass 38 kilograms released from rest at point A on an incline. ABC is a frictionless section. That's a very important piece of information. It's a frictionless section, and CD are a rough section of the incline. So when it says frictionless, the implication is that the mechanical energy is conserved. That's the implication. The trolley reaches point B at the incline at a speed of 1.5 meters per second. So this is the story and this is the situation. So between point B and point C, there is no friction. So that means the net work done, or rather, there are no non-conservative force. It's frictionless. So the situation of frictionless gives the idea that the mechanical energy is conserved. But the first part are your definitions. 5.1, define the term a non-conservative force. And I think 5.2 says name the non-conservative force. I did that in the previous question, I think, but basically it's a force for which the work done in moving an object between 2 points is dependent on the path taken. That's 5.1. 5.2, name of the non-conservative force, it's frictional force. That will be the answer for 5.2. So it's path dependent. It's definitely non-conservative. Somebody has a question, go ahead. I want to hear what you have to say.
Hello, sir.
Hi.
Hi. I have a question. In fact, it's more of like a can you explain type of thing. So can you
Maybe
please
get close to the
explain?
mic because you're a bit muffled. I can hardly hear you.
Okay, hold on. Can you hear me?
Yeah, it's better now.
Okay. So can you please explain in depth what a non-conservative force means? Like in depth, because I can memorize it, I've got it, but I really don't understand what it actually means.
Okay, fine. I'll do that. All right. So just to reiterate the issues of non-conservative and conservative. So let's say this is point A, and this is point B. The object wants to move from A to B. So it can go this way. Let's call this path 1. It can go that way. Let's call this path 2. It can go that way. Let's call this path 3. So there are many different paths and ways in which objects can move from A to B. If a conservative force acts on this object as it moves between A and B, if it's conservative, the work done by that conservative force will not be affected by the path taken. So you may take path 1, you do the same work, conservative. You can take path 2, that force will do the same work. You can take path 3, the same amount of work. That is a conservative force. The path taken is independent. But if it's non-conservative, then it means where you go, the path that you take will affect deeply the work done. In essence, the work done by path number 1 is not the same as the work done by path number 2, by path number 3, if it is non-conservative. But if it's conservative, work done by path 1, work done on path 2, work done on path 3 is the same. And that basically is how you explain the story. All right, 5.2, we said frictional force. 5.1, we defined. 5.3, and we are going further. Point C, there we are, is a point on the incline, 0.75 meters lower than point B, sharp. Calculate the speed when the trolley reaches point B. Follow my lead, I got your back. So we're looking for the speed when the trolley reaches point B, point C. Since it's frictionless, then the mechanical energy would be conserved. So the Emac at B should be equal to the Emac at C. By the way, this will only work if the surface is frictionless, which means there are no non-conservative forces acting on the object. What you have in terms of mechanical energy at at B, is what you also have at C. In that regard, mechanical energy is basically the sum of the potential energy and the kinetic energy. That's what Emac basically is. So it's the potential plus the kinetic energy at point B equals similarly to the potential plus the kinetic at point C. Here we go. And then let's start with the potential. As a formula, it's mg H, we usually say H initial, because that's where we're starting at B, plus U half mv squared I initial as well, is equal to mg H final plus U half mv F squared. All right, so I need you to listen to this. Whether you write it this way, first way, second way, or third way, you still get 1 mark. So you can't write 3 different versions of the same thing and get 3 marks. No, Chuck Norris. It doesn't happen. Let's put numbers together. The mass is 38. G is 9.8. So the initial height in comparison to where we are, we're supposed to be at C. So the initial height of B is actually 0.75. If you consider the section BC, 0.75. So 0.75 plus it was at rest. It started at rest. So that gives you typically an answer for so it was done from rest at A, but then at B, it was 1.5. So it's going to be a half. The mass is 38. And I think we're looking at 1.5 squared. Then the mass are now again equal to, the mass is 38, G 9.8, but at C, you're at the point of reference, so your height is 0, plus a half, the mass again 38, and what you are looking for is the velocity right here at C. Doing your maths properly, the final velocity is 4.12 meters per second right there. There's many options. You can use work done by a non-conservative force. You can pretty much use all of that and you'll be able to get what you need. Please do confirm my answer for 4.12. Is that what you guys got? Please do let me know so I can be of assistance. Go ahead, I'm listening.
Yeah. Can you hear me?
Yes.
Okay, so may you please use a different formula? specifically the WNC is equal to delta EK if it's applicable, because that's what I used.
Like I said, there's thousands of ways of doing this. Well, about 6 ways of doing this. And if I run through all of them, I will not finish, right? But let me try and show you how this one works. You get the same answer eventually at the end of the day. All right, so that you may know, guys, I'll send you the memo. You guys can be able to see this. Otherwise, I'll end up doing 1,000 ways because all of us did it in different ways. So work done by non-conservative force is change in the mu, U, and change in E, K, or you can say K, like this. So it's 0 because there is no non-conservative force. So it's going to be mg here, hf minus hi plus uk is going to be a half m vf squared. This is the other method, guys. Vi squared. That's 0. The mass 38 times 9,8. Final is 0. Then 0,75 plus U half. The mass is 38. Then final velocity, don't know it. Initial was 1,5 squared. You're just looking for VF. You will get the same answer. Just to confirm, I think it's 4,12 meters per second. That becomes your answer in that regard. Go ahead, ask me. I'm listening.
Okay, so in the previous working, we used Emac B equal to Emac C. Ne?
Yes.
I would like to ask, why was the MGH for C 0? Like I assumed it'd be 0, but I wanna understand why is it 0. Why is it correct to assume that it's 0 in this situation?
Okay, it's because your end point is C. You see, your reference is from B to C. That's where your referencing is. So like from here to there, and then like that, and then like that. So when we reach C at my point of end, at my end point, in relation to B, I am actually at 0 meters, and B is 0.75 away from me. It's as if, thank you for that, because it's as if this line, this dotted line is the ground. It's as if it's the ground. And when you are here at C, you're at your final point in reference to where you're coming from, B. So therefore, it's going to be 0 in that regard.
Okay, so let's say that calculate the velocity or speed from A to B, and we have A's height, and then B would take as what, the ground.
Yes, from A to B, then B would be 0. It would be definitely at the ground. And only, remember, you can only use this if A, B, the track is frictionless. And it's otherwise.
Okay, so if it wasn't frictionless,
you
it
wouldn't.
would be impossible to take B as the ground, referencing it to
Not
A.
necessarily. If it wasn't frictionless like CD, we can't use this formula of Emac top is Emac bottom, because the formula for Emac is only applicable under a situation where it is a frictionless surface. So you'll see when I do CD, I'll use different formulas because the frictional force is now there. It's a rough section, so it will be there.
Oh no, that I understand. I'm just saying that regardless of whether it's a frictionless path or whatever path, we can take B as the ground, referencing it to A.
Yes.
Okay, sir. Thank you.
Perfect. All right, let's go further on that one. Somebody else has a hand. Go ahead. I'm listening.
Can I ask about something else? May I use the work net is close to changing EK? So I want to ask about I want to ask about the cause of FG parallels. It's going to be 0 or 180.
It's going to be 0 because the object is going downwards. And you see the object goes down, And the force of
Yes.
gravity parallel also acts downwards. So it's going to be 0.
Okay.
You're asking about the theta for all cos, right?
Yes, for cos. Yeah.
Now it has to be 0 because it's moving in the same direction as the displacement. That's why.
I didn't get the same answer. Okay, I will check my mistake.
All right, send your answer to the group. I'll run through it very quickly. All right, let me take another last hand, then I can continue with the question. Go ahead.
Sawubona sir,
Hi.
uphilile?
Right.
Nami ndi-right. Sir, bengicela ukubuza la ku-question eka 5.3 ya.
All right, so you can
Mina
count.
like
Maybe let's use English because you know how it is. We're all very different, so we can try that. Ne? So that'll be fine.
yes, sir.
Okay, you're saying
So
5.3.
sir,
Uh-huh.
yes, 5.3. I used a different formula like the equations of the motion instead of the Emac. The summation of Emac initial is equals to the summation of Emac final.
What did you use for your acceleration then?
I used 9,8.
But if you do that, you're now assuming that the object is a projectile, and it's not. You see?
Yes,
So if you use 9,8, then you're assuming that the object is a projectile. And I'm saying, no, the
yes,
object
sir.
is not a projectile. Yabon.
Yes, sir.
All right. So that's maybe where the problem is. All right. Allow me to just go to 5.4 quickly, and I will come to the
But-
next set. Yeah?
But I still got the same answer though. So kusho ukuthi next time I shouldn't like assume ukuthi like maybe the acceleration it's 9,8.
Yes. You can't assume that
Okay,
unless
sir.
you're told. Yes. And maybe just, and thank you for that. Maybe just to reiterate to everyone so that everyone can
Yes, sir.
understand. Listen, fam. In physics, you can get the right answer, mathematically correct, but physically wrong. It's like getting into the house using the window. Yeah, you're in the house, but that's not how we get into the house. People use the door. So mathematically, you can't be correct, but physically, cha, ayabona ungatrim, all right? Physically, it's not working, all right? So that basically is the backdrop of all of that. Allow me to go further to the next one. And all. Please do confirm the answers to the previous one, so that I'm okay with the movement. Here we go. The coefficient of kinetic friction between the trolley and the surface of the section, CD, is 0.21. The trolley comes to rest at point D, and then it says calculate the magnitude of the kinetic frictional force acting on the trolley as it moves from point C to D. So at point C to D, we now have friction. And so if you gather your story from C to D, if you're looking for the friction, and I did say this, Uguti, when looking for friction on an inclined surface, is mu k mg cos theta. That's what I said. Mu k mg cos theta. So it's going to be 0.21 multiplied by the mass, which is 38, g 9.8 multiplied by cos 10. Remember, for this formula, the theta is the angle of inclination. And so your final answer is actually 77.02 newtons. Give me a confirmation of that one, please. Let me know so that I can see if we're on the right track. All right, perfect. Thank you. Let's try the next one for H. Let me hear your answers for H. What did you get for the value of H? Ooh, that's an interesting one. What you get for your value of H, please type down your answers. Let's see. 0.84, 4.53, 4.54, 0.84, 0.9. It's like the lotto. It's like the lotto. Every number's unknown. Unknown. How? 0.87, blah, blah, blah. It never stops. 6 marks. Let's do this, Ndwana. Like you guys are giving the Powerball numbers. Right. Let's see if we are winning in that regard. So use energy principles only to calculate the height of H. Okay, sharp. So the height of H, which is basically from C, it's the same level like C, up until I get to the ground. I can even write it like this as H, which is fine. Put it there. Yeah, which is that. So then it goes on further to say use energy principles. Let's clarify what happens between C and D. So the object is moving downwards. It's released from point A to all the way downwards. I want you to understand that in this story, there is no applied force. No one said to us a force was applied to move the object down. In fact, by virtue of being on an incline, when you release something on an incline, it just simple moves down on its own accord. So from point A all the way downwards, what is moving it down is the force of gravity parallel. That's what's busy moving this object downwards. And do remember, at all aspects, the force of gravity parallel is always acting down. In comparison, friction, in this case, will oppose the displacement of the object. The frictional force is acting to upwards, and then you've got your normal and your gravity perpendicular, which eventually cancel out. So using energy principles, I'll use the work-net formula. You can do any other, but that's still fine. The network is delta, it's called delta K. Who's doing work is the friction. Who's doing work is the gravity parallel. All this is equal to half mvf squared minus the half mvi squared. So we're looking, remember, for the height of H. Now, the work done by friction is force of friction, delta x cos theta. The work done by gravity is basically mg sine theta, and then delta x, then what? Talk to me, cos theta. Then you've got the half mv f squared minus half mv I squared. I'm looking for H. Perfect. Follow my lead. Now, there's so many ways of doing this, but let me show you how I would think about it. You see, H is this height. Ne? That's what H is. And so if I was to draw it as a nicely built triangle, I would then have a situation where this would definitely be 90. It's a straight line that goes straight up to the ground. And this is your theta. Let's say this is your theta. And this is your CD, right? So then mathematically, this is H. It would mean sine theta is the opposite, which is H, over the hypotenuse, which is CD. Now, CD in this work, energy, and power would be your delta X. That's what CD is, your delta X. So if you were to bring across the idea, you would say, but sine theta is H, which is what I'm looking for, over delta X. Somebody asked me a question, to say, can we do a question where you're looking for the angle? And I'll tell you this and now. I have another YouTube video on work, energy, and power. I'll tell you this and right now. The way I'm doing it now is exactly how you get the theta. But here, at least we're not looking for theta. We have it. We are looking for OH. That's what we're looking for. Let's do some maths right there. Put some numbers and see if on those numbers we can be able to win and take it up from there. Follow my lead. Okay, let me put it here. Just a bit closer. There we go. We start. So I'm here now. We're bringing this guy down here. So I don't know what H is. I don't know what CD, which is delta X, is. So I'll just write it down. FF, I think I know the force of friction from the previous answer for 5.4, I think. Yes, it is 7 point, I think, was it 02? Something like that, multiplied by delta X, which I don't know, multiplied by cos 180. Keep remembering Guti friction is acting opposite, so it's going to be 180. Then M, the mass is 38, G or 9.8. Then sine theta, we know it as 10, sine 10. All right, let me write it down. So there you are. It's going to be sine 10 multiplied by delta X, which I do not know, and then multiplied by cos 0. The reason why the force of gravity parallel has theta as cos 0 is because it's acting in the same direction as the displacement. Then half, then the mass of the object, again 38. The final velocity, we are told that it definitely comes to rest at D. So I'm looking at 0 squared minus a half. Then that's 38 again. Then the initial velocity, which is the one at C. Remember our starting point this time, it's C. So I remember from the previous one, we calculated what happened at C in 5.3, and we got an answer of 4,12. So it's going to be 4,12 squared. The only guy that we don't know is delta X. That's the one that we don't know. We do the maths, you end up with something with a delta X here and something with a delta X. You add them together. You'll eventually have to divide so that you can get the delta X. If I'm not mistaken, my value for delta X is 26,11. And then from here on, I can now then find what H is. All right. So then now that I know delta X, and then I can find H, sine theta, sine 10 is H over 26,11. And the value for H, as some of you guys got it right, is 4,54 meters. That's your answer. That's how you roll. That's how you do this. Talk to me now. Talk to me. Right. While I pull through, somebody has a hand. Let me attend to that. Go ahead, please. I've unmuted you. All right, seems like you're not available anymore, but still, that becomes the ultimate answer to this question. Do you guys get it? Do you understand? Do you see where I'm coming from? Oh my word, what a session, what a time. What a time, what a session. All right. So next week again, almost does count. Yes. Luckily, we got part marks. And so don't ever give up on yourself on anything. You guys have a lot to win. You look at the situation at home, you'd want to make sure you change it. You have a future that you need to beckon to. You want to change it. You want to have a great future. It all starts with good decision making. Good decisions make good futures. And bad decisions, in the same breath, they make bad futures from that perspective right there. I've unmuted you for the second time. Please say something.
Hello, sir.
Hi.
Okay, so in terms of finding H, I used the formula. Okay, at first I had to find FK, and then I got my FK as 77,0159 Newton. And then I found CD the same way. I said CD is equals to H over sine 10 theta by using trig functions. And then I used the formula WNT is equals to change in EK plus change in EP. And then I got my height as 4,67 instead of 4,54.
Okay, maybe send that to me. I want to see how far you went. And you said you found UFF, but remember you found it from 5.4. So you had to
Yes.
refind it. So it's fine. So just send it to me, then I'll check and confirm. It could be an error of 1 or 2 digits off, but yeah, I think I would approve your typical method. All right. That being said, okay, I'll just send it to me, then I'll confirm and also update people on YouTube and WhatsApp on that on our WhatsApp group as well. All right, so somebody also has a hand. Go ahead, I'm listening.
Hello, sir.
Hi.
So I wanted to ask you something about that formula double net. No. Yeah, when you're calculating double net, ne? So
Yeah.
if you are starting by calculating the F net equals to MA, ne?
Yeah.
And then you find a positive answer.
Yeah.
Ne? What do you write on the angle? And what do you write if you find the negative answer?
If you want to find a positive answer, then that means your theta was 0. And if it's negative, it's 180. But again, for you to eventually say F net is positive, that means you must have concluded that the direction upon which the object is moving is where you got the biggest force. So that means F net will be positive. But if it's negative, then it must be the opposite way. So I'm thinking you are saying to me, work net is equal to F net delta X cos theta. Then for F net, in this case, it would be FG parallel minus FF, then delta X cos theta. Definitely the theta will have to be 0 because the biggest force is force of gravity and is acting in the same direction as the displacement. So you'll have a work net as 0. Are you okay on that?
Yes.
All right, perfect. All right, so that's good. Probably our last hand of the day. Go ahead.
Hello, sir.
Hi.
I just had a request. Could you please send the recording to the group?
I'm going to upload this on YouTube.
Oh, okay. All right.
Even better. All right. Okay.
Thank you, sir.
Anytime. All right, fam. Thank you so much. I appreciate. So I was talking about making good decisions. Guys, we are on lockdown now. You are breathing, eating, walking, talking, seeing, wearing, bathing, thinking, dreaming, school. Your name is school. What do you eat? School. What do you love? School. Where do you stay? School. What do you want to be? School. What is your biggest crush? School. Everything about you is school. What perfume do you put on? School. What type of roll-on do you have? School. What's your favorite pair of sneakers? School. That's exactly who you are. You are nothing but school. Exactly. School is all you know, and the school is all you're going to do. So after this, we're going to school. Tomorrow in the morning, school. As we walk out of school, school. Even in the taxi, school. Yonke into school. Azo. The only way to pass is to do things that you have never done before. If you want marks that you've never gotten before, you must be willing to do things that you've never done before. You are not going to take 1 year of work and try to memorize it in 2 weeks. Who are you, Chuck Norris? Who are you? So whatever you need to do, make sure you do it well with your heart, your soul, and your mind. Make good decisions. And part of good decision making is attending the Mr. X online classes. The ones that I'm having online on the top right corner, and the one on the left-hand side of the face-to-face. Face-to-face is 1,000 rands. You guys have not seen how fiery I am until you've seen me face-to-face. Some of you see me on TikTok. Those guys are just seeing me for 3 minutes or so. Imagine if you were with me for 8 hours a day. for 4 days for a cost of 1,000 rands for that particular time. Damelin College face-to-face. These are the groups available. Group 1, Group 2, Group 3, as you can see from the poster. If you're not available face-to-face and can't make it, maybe you're out of Johannesburg, don't worry, I still got your back. But this time is a 20-hour program, and it's an online 500 rands per subject for 20 hours. In my culture, when someone does something nice for you, we are bonga. You say thank you. Magwande. Zandla zedlulikhanda. That's what we say in my culture. And I hope you guys learned and appreciated everything that we did today. Let's make sure that we work extremely hard, pull through, and don't forget to write the nice comments even on the group. Just so I use them for my social media so that everyone can, you know, pretty much pull through. Then one last thing that I want and ask of you is, if possible, just type where you are, the province where you are. Just want to see where people are. Online is very interesting. Let me hear where you guys are, the province where you are. There's Limpopo right there. Lovely. And Gauteng, then all that. KZN, lovely. Beautiful places where you guys are. Appreciate where you guys are, what you guys are doing. May God bless you. May God keep you. And may we work extremely hard. I will stop the recording now.